Let's do it.
All right. So this week's topic is we're going to start off with greatest common divisor and least common multiple. So first, we're going to go over the definition. The greatest common divisor, which is often abbreviated as GCD, is defined as the GCD of. Shoot, I'm not good at this. Just give me a second. The GCD of two numbers. Oh my God, I'm so bad. A and B is defined as the greatest number that divides A and B. So a quick example, we're just going to go with GCD of 12 and 15. And then this is going to be 3, because 3 is the largest number that divides both 12 and 15. So next, we're going to go to least common multiple, which is abbreviated as LCM. And the LCM of two numbers A and B is the least number that is a multiple of both A and B. So going back to the example, if we take the least common multiple of 12 and 15, that's going to evaluate to 60, because 60 is the least number that's a multiple of 12 and 15. All right. So we're going to go. Okay. So the way we get to 60, we can easily get to 60, is we list the multiples of 12. So we can see that it's 12, 24, 36, 48, and 60. And then if we list the multiples of 15, we get 15, 30, 45, and 60. And we see that 60 is the least number. That's a multiple of both of them. So the LCM of 12 and 15 will give you 60. Now let's get to ways of finding the GCD and LCM of two numbers. So we learned last class the basics of like prime factorizations, and that's going to be useful when trying to find the GCD and LCM. I'm going to write some notation first, and this might be complicated, but I'll explain the notation later. So if we have two numbers, A and B, and their prime factorizations are P1 to the A1, P times P2 to the A2, times P3 to the A3, all the way times P of n to the A of n. And B is similarly defined. And this is just the prime factorization notation we used last class. Then we have the GCD of the two numbers is simply P1 to the minimum. So the min of these two numbers is simply just like the minimum of A1 and B1 times P2 times to the power of the minimum of A2 and B2. And we just continue this until P of n. And similarly for the LCM, we do the same exact thing. Oh, but not min. What am I doing? We do the same thing, but instead this time we use the max of the two numbers, of the two exponents. So this might look complicated, but I'll show you with the example, and this should make it easier to understand. So first, let's practice finding the GCD of 126 and 420. And similarly, let's find the LCM while we're at it. So the first step we're going to do is we're going to prime factorize both of these numbers. So we have that 126 is just equal to 2 to the 1 times 3 to the 2 times 7 to the 1. And we have 420 is equal to 2 squared times 3 times 5 times 7. And we can just have the exponents of 1 just to make them easier to see. So based on this definition, for each prime, we compare the exponents on both of the numbers. So for example, if we look at 2, we have 126 has an exponent of 1 and 420 has an exponent of 2. So for the GCD of 126 and 420, we first take the smaller exponent of 2. So we have 2 to the 1. And similarly for 3, we take the smaller of the two exponents, and we see how there's a 2 here and there's a 1 here. So we're going to take the smaller one. So it's times 3 to the 1. And then now we go to the 5s. We see that 126 doesn't have a factor of 5. But instead, yeah, like Hansen said, anything to the power of 0 is simply 1. So we can imagine this as having a 5 to the 0, since multiplying by 1 has no effect on the number. So again, we take the smaller of the two values, which is 0. So we can write 5 to the 0, but since it's 1, it doesn't really affect the GCD. And then similarly, we do this for 7. But we notice for 7, both of the exponents are 1. So it doesn't matter which one we take, because they're the same thing. So we just take 7 to the 1. Does that make sense to everyone? Okay, everyone's saying yes, so I'm going to continue. We go to least common multiple of these two numbers. We're just going to do the same exact thing, but instead of taking the smaller exponent, we take the larger exponent. So we compare the 2's again, and we see this one has an exponent of 1, while the other has an exponent of 2. So we take the larger one, which is 2. And similarly, we do this for 3, and then 5, and then 7. And again, 7, both of them have an exponent of 1. So it doesn't really matter which one we take. And then we can just multiply these out if we wanted to. I'm bad at mental math. I think this is 1260. So that's one way we can find our GCD and these common multiples. There's another cool property that we can see. Of least common multiples and greatest common divisors. We have of any two numbers, A and B, integers, of course. We have the greatest common divisor of A and B multiplied by the least common multiple of A and B is always equal to A times B. And this can be easily shown by looking at the definitions. So if we, when we multiply the least common divisor and the greatest common divisor and the least common multiple, we see that one of them has the min of A1 and B1, and the other one has a max of A1 and B1. So when we actually multiply these two terms together, since one of them is larger and one of them is smaller, we always get one of them as A1 and then the other one is B1. So when we multiply them, we simply just get P1 times A1 plus B1. And simply on this side, AB is when we multiply them, we get the same exact thing. So if we do that for every prime, so for P2, one of these is A2 and one of these exponents is B2. And similarly, when we multiply A and B, we're going to get the same thing. So for every prime, we're going to end up with the same thing on both sides. So that shows that these two are equal. Sorry if my explanation was bad. That makes sense, right?
Yeah, basically.
Okay, don't be scared if you have any questions for me. We're gonna go to a method of finding the greatest common divisor of like really large numbers that you don't want to prime factorize. To be honest, this method is probably most of the time on like AMC8 and math counts, it's probably slower than just prime factorizing both of them. But we're gonna show it just for people who like want to see like a more advanced method. And I think it's gonna be more useful like later on in like other contests. It's called Euclid's algorithm or Euclidean algorithm. So basically the Euclidean algorithm states that the greatest common divisor of A and B is equal to the greatest common divisor of A minus B and B. Yeah, a lot of things are named after Euclid, like the Euclidean plane, as you guys just said. So at first glance, the statement looks like, it doesn't look that useful. It's just, it looks kind of dumb. But we're gonna see that this statement is actually very useful in computing the GCD of large numbers. So if we go back to our original question, GCD of 420 and 126, we can use the previous method of just prime factorization and then just like comparing the exponents and stuff. But we can also apply, sorry about that, the Euclidean algorithm. So that states the GCD of 420 and 126 is also equal to the GCD of 420 minus 126 and 126. So we can simply just evaluate that and get 294 and 126. And as you can see, we've lowered the numbers quite a bit. And if we just keep on doing this, like we keep on subtracting 126, we get 168 and then 126. And if we do that again, we get the GCD of 42 and 126. And we notice that we can't take any more 126s away from the 42 or else we'll get a negative number, which we don't want. So we can simply take the 42 away from the 126 this time. So it's just GCD of 42 and 84, which is, if we applied the Euclidean algorithm again, we'll get GCD of 42 and 42. And then this simply evaluates to 42 because the GCD of two of the same numbers is just the same exact number. So as you can see, we got the same answer as we did above, except this time we don't have to prime factorize everything. We just perform a couple of subtractions. And like this probably is the most useful for math counts in AMC. You can use it to like double check and stuff. But it'll probably be useful like later on for like AMC 10 and like stuff like that. And now I'm going to introduce another topic that's really important. It's something that doesn't seem super important like at first glance, but it comes up a lot in AMCA and math counts. So we're going to go over modular arithmetic. So first, we're going to go over the definition of a mod. So if we have the number a mod n, this is equal to the remainder when a is divided. Oh yeah, it's also the percent sign encoding, which is very useful if you want to like do coding competitions. It's the remainder when a is divided by n. So simply, it's just like when you're in elementary school and you just practice division, and it's basically the remainder that comes out. So quickly, like 77 mod 5, we simply have 77 is equal, this is equal to 2. Because the remainder when 77 divided by 5 is just 2. So like, how is this ever useful in math competitions? We have a lot of cool properties about modular arithmetic that can simplify our work. For example, if we have two large numbers, a and b, and we want to multiply them, and then we want to find the remainder when divided by n, we have this cool property that this is just equal. We can take the mods first. So for example, we can do a mod 5, mod n multiplied by b mod n. So like a quick example would be like, what's the remainder when like 51 times like 97 mod 10. So this is a basic question because we can just take 51 mod 10 multiplied by 97 mod 10. And this is just equal to 1 times 7, which is just equal to 7. So we have this whole product is equal to 7 mod 10. Do mods make sense to everyone? Or are there any questions? Anita, do you have any questions about it?
Just don't really understand it. No.
Okay, so you understand like the definition, right? Do you understand why 77 is 2 mod 5? It's because like the remainder when 77 divided by 5. So if we just perform the division, we're all familiar with this, right? I'm gonna hope you guys are familiar with this. So we have a remainder is equal to 2. That's all it is. Okay, that's basically all mods are. They look complicated, but like that's basically all it is. You're just dividing by number and taking the remainder. We'll go into some more advanced questions that use this later. But yeah, I think that's all for the lesson. And then we're actually going to go to solving some questions now. So let's start off easy. This is just 2013 AMT8 number 10. So it says, what is the ratio of the LCM of 180 and 594 to the GCD of 180 and 594? So I'll give you guys like a minute or two to try this out. But if you guys prime factorize both numbers, you guys should get the answer. Okay, Hanson got the correct answer. Okay, Adam got the correct answer as well. Good job. Are you guys ready for me to go over the question? Okay, someone said no, so I'll wait like 1 more minute, just so you guys can try it out. Okay, so on AMC 8, you guys only have like 1.5 minutes for each question, and this one's like one of the earlier questions, so you guys should be able to solve this one in about like, I don't know, a minute probably. So I'll show you guys a really fast, well, not a really fast, but like just how to do this if you were doing it on the test. So first off, we should prime factorize both of the numbers first. So 180, we notice that 2 divides it, we get 90. Another 2 divides it, we get 45. So 45 is just 9 times 5. So that's a prime factorization of 180. 594, the 9 looks so bad. 594, I'll just tell you guys, the prime factorization is 2 times 3 cubed times 11. So for the GCD of 180 and 594, we look at the smaller exponent. So 2 to the power 2 and 2 to the power 1, the smaller one is 2 to the power of 1. For the 3's, the smaller one is 3 to the power of 2. And for the 5's and 11's, they're both to the power of 0, so we don't have to write them. The least common multiple of 180 and 594, we write the larger exponent of the two. So it's going to be 2 to the power of 2 times 3 to the power of 3 times 5 times 11. And the question asks, we actually don't have to compute these because the question asks for the ratio of the LCM and the GCD. So basically it's asking for the LCM divided by the GCD, which is, we can take a shortcut and instead of multiplying these out, we can just simply write them as a fraction. And we can cancel out the denominator. And we get this is equal to 330. So that's going to be the answer because it's the ratio. Is there any confusion on this? Okay, everyone seems ready to move on. So we can just move on to the next question. So this is where modular arithmetic starts. So there's a lot of questions on AMC and math counts that says like, what is the unit digit of like this very large product? And just to make sure, this sign, this caret sign thingy, it just means to the power of. So for these unit digit questions, we want to find the product mod 10 because mod 10 is the unit digit. So like if we have like this number 323, if we take it mod 10, the remainder when divided by 10 is just the unit digit, which is 3. So basically in modular arithmetic, this question is asking for the unit digit it's asking for this product mod 10. So 7 to the 23 times 8 to the 105 times 3 to the 18 mod 10. So a nice property of mods is that you can separate the numbers, like you can separate these numbers products and then take a mod 10 and then multiply them all together afterwards. So for example, we can take the 7 to the 23 mod 10 first. And for these singular exponents, there's always a pattern like that repeats in cycles of 4. So for example, if we look at 7 to the 0, which is equal to 1, its last digit is 1. And if we look at 7 to the 1, it's going to be 7. And if we look at 7 to the 2, it's going to be 49. So the last digit is 9. 7 to the 3 is 343. And the last digit is 3. 7 to the 4 is 2401, which is last digit 1. And if we go to 7 to the 5, we'll notice that it's also 7. Because 7 to the 5 is equal to 7 to the 4. Oh my God, what am I doing? 7 to the 4 times 7. So if we take this mod 10, the 7 to the 4 is simply just equal to 1. So we can cancel that out and we get 7 to the 5 is equal to 7. And we can see that easily 7 to the 6 is also equal to 9. And we can see that it repeats in cycles of 4. It goes 1, 7, 9, 3, 1, 7, 9, and so on. So if we look at 7 to the 23, it has a 23 has a remainder of 3 when divided by 4. So what that means is we can simply look at which one of these it is. Since it's 3 mod 4, we look at this product. So 7 to the 23 is just simply congruent to 7 to the 3. Oh, okay. Yeah, I might have gone too fast. So Hanson asked, why did you divide by 4? Okay, so the reason we divide by 4 is because it loops in cycles of 4. So going back, if we take 7 to the 0 equals 1, oh, and Esther asked, why am I writing 3 lines for the equals? 3 lines indicates that they're congruent. Congruent means like they're equal to a mod number. So we have 7 to the 1 is equal to 7 mod 10. I just won't write the mods because I'm lazy. And we have, it saves time. And 7 to the 2 is congruent to 9. 7 to the 3 is congruent to 3. And 7 to the 4 is congruent to 1. And we can see that it just starts cycling. If you want to continue, we can see that it cycles. I'm reading the chat right now. Okay, so we're finding the last digit of all of these powers. Oh, the question? We want to find the units digit of that product. We separate the product into 3 parts and we're working on the first part right now. So just to give you, I'm just going to tell you that these exponents always cycle in cycle of 4. So basically, we just have to see which number of the cycle this number corresponds to. And this number corresponds to 3 because it has a remainder of 3 when divided by 4, which is the length of the cycle. So basically, we have 7 to the 23. The last digit, or like its value mod 10, is just 3. And now we can just continue this for the other 2 parts. So now we work on the 8 to the power of 105. I've told you that all these numbers, like the last digit, form cycles with length 4. So we can just simply look at the first few terms. Oh, so we go 8 to the 1, the last digit is 8. 8 to the 2, the last digit is 4. 8 to the 3, the last digit is 2. And 8 to the 4, the last digit is 6. So the way we can find this fast is we can just multiply the previous number by 8. So like if we have 8 here, we can get 8 times 8 is equal to 64. And the 4 goes here. And then to find the next number, we can do 4 times 8 is equal to 32. And then the 32 moves here. And then the 2 times 8 and so on equals a 16. And we move the 6 here, and we have 6 times 8 equals 48. So 8 to the 5 has the last digit of 8. And we can see once again that this forms cycles of, it's going to repeat in cycles of 4. So once again, we take the exponent 105 mod 4. This is just a fancy way of saying like what's the remainder when divided by 4. And we have, it's 1. So we have 8 to the 105 is going to have the same last digit as 8 to the 1, which is just simply 8. Mod 10. Okay, a lot of people are forgetting the question, so I'll go back to the question really quick. Okay. It's just find the units digit of this fancy product. Okay, yeah, thank you, David, for posting in the chat. So we've already found the 7 and the 7 to the power of 23 part, and the 8 to the power of 105 part, mod 10. Oh, yeah, the caret symbol thing that you see. So we have 7. You see this symbol? This is just equal to 7 to the power of 23 as an exponent. Sorry. Okay, I'm gonna let everyone else try the last part of the product, which is 3 to the 18. Can you guys try finding the last digit of 3 to the 18 using the same method we did here? Guys, I don't think coding is going to be useful in a math competition. but it's cool that you guys know how to code. Can you guys try finding the last digit of this? Okay, I'll wait like 15 more seconds. Oh, I'm sorry. Oh, I do this. I forgot to answer this question, so I'm just doing this like live. So I can't really confirm if you're right. Okay, so most of the people in the chat are done. I see mostly nines, like some sixes and sevens. Oh, Anita, we're not finding what it's equal to. We're finding the last digit. Okay. So let's start. We can do the same method we did above. We just go through the exponents and see the pattern as we like the cycle basically. So 3 to the 1, the last digit is 3. 3 to the 2, the last digit is 9. 3 to the 3, the last digit is 7. And then 3 to the 4, the last digit is 1. And you can memorize that the cycles are always 4, but if you forget, you can just keep on checking, and 3 to the 5, you'll find equal to 3. What's this line doing here? Okay. So we can see it's a cycle of 4 once again. So this is the cycle. So 3 to the 18. Why is there this line? That's kind of, okay. Wait, where'd that go? Okay, sorry, I'm kind of bad at using this. Okay, I'm just going to ignore that. So we're going to see which number 3 to the 18 matches to. And 3 to the 18 is just equal to 3 to the 2, which is equal to 9. And we got to the 2 because we take the remainder when it's divided by 4. Does that make sense? Okay. So we're going to go to computing the final answer. The product of these three large exponents mod 10, we can take the mods first and then multiply the 3 numbers. That's going to be really easy. Right? So we have 7 to the 23 is equal to 3. We have 8 to the 105 is equal to 8. And we have 3 to the 18 is equal to 9. Right? So we have 3, 8, and 9. So this final product just evaluates to 3 times 8 times 9. Mod 10. And then this unit digit, you can just multiply it all out, and you get 72 times 3, whatever's in front. The unit digit is 6. So like the final answer will be 6. We can see how modular arithmetic simplified this question down a lot. You're talking about programming. So here's another similar question that you might see in math counts. This one's a bit harder. It's a states number 28. But it's still not too bad once you know what to do. So it says, what's the remainder when 11 to the power of 12 is divided by 13? And we can interpret this as taking the mod 13. So what we learned is we can take the mod of the base. 11's kind of big, right? So we want to make that smaller into something that we can easily compute. So we have this cool identity. We can use negative numbers in this case. We have 11 is congruent to negative 2, mod 13. And this is because we can just subtract 13 from 11 to get to negative 2. Okay, if you're like having a hard time understanding why we can have this to be true, let's think of all the positive numbers that are 11 mod 13, right? So we can have 11 is 11 mod 13, but we can also add 13 to this number. So 24 is also 11 mod 13. We can add 13 again, right? And we get 37 is 11 mod 13. And then we can keep on going to the positive side forever. And that makes sense to like everyone, right? But instead, we can go backwards as well. Instead of going to the positive direction, instead of going this way, we can also go this way from 11. So we can subtract 13, right? And we'll get to negative 2, negative 2. And then we can subtract 13 again, and we can get to negative 15. See, all of these are congruent. All of these numbers are congruent to 11, mod 13. Okay, are there any questions about this? Okay, I think the chat looks like they're getting it, so I'm going to continue. So since these are equal to mod 13, we can simply replace the 11 with a negative 2. So instead of finding 11 to the power of 12 mod 13, we can change this question to negative 2 to the power of 12 mod 13. Okay? So since 2 is a small base, and then 12 isn't that big, we can just like compute this value. And we can just find, so we have negative 2 to the 12 is just equal to 40, 96. Right? And then basically to find the answer mod 13, we can just do a quick division, long division, right? Oh, I haven't done this in a while. I might screw up. Okay. Yeah, good job, Emma. The answer is 1. because the modular is just the remainder. Okay, yeah, I can slow down a bit. I'll go over the process again. So one property of mods is we can basically replace the base number right here with any number that's equal to it mod 13. So we can replace the 11 with a 24 or a 37 or like any number, any one of these numbers. But we want to pick a smaller number so it's easier to compute. Does that make sense? And since -2 is fairly small, we can easily compute this value right here. Okay, everyone understands this question, right? Okay. Oh, Eric asked, why can we do that? Okay, so we have this property that for any numbers a times b. Oh, okay, sorry, I didn't say the question. The question is, why are we allowed to replace the 11 with a -2 from Eric? And I'll go over the basics. We can use the fact that we use our original property that a times b mod m is equal to a mod m times b mod m. So in this case, we have 11 to the power of 12, right? We can pretend that this is 11 times 11 times 11, 12 times 11. And no, we can take, oh, why is that true? Oh, that's a bit long to explain, but for now, we can just assume it's true, okay? And we can just replace all these 11s with -2s. Oh, also, if you're curious about why this is true, you can just send an email and then I'll respond to you later. So basically, we can replace all these 11s with their with any number that's their mod. So doing this, we can simplify this to -2 to the power of 12. Okay. We're going to go to this classic question. It says, what are the last 2 digits of 7 to the power of 2020? So last 1 digit is equivalent to taking the mod 10. The last 2 digits would be equivalent to taking the mod 100. So basically, this question is asking us to find 7 to the power of 2020 mod 100. Right? So the key idea of this question, you guys might have to memorize this trick, but you have to realize that 7 to the power of 4. Oh, I wrote 1000. My bad. Yeah, nice catch. It should be 100. So the thing we have to realize about this question is 7 to the power of 4 is just equal to 2401. And taking the mod 100, we get this is equivalent to 1 mod 100. Since so using the basic rules of exponents, we can write 7 to the power of 2020 is equal to 7 to the power of 4. And then we take the whole thing to the power of 505. Why are we spamming XDs in the chat? Okay, and from the property before, we can replace this base number with any other number that's equivalent, mod 100. And so once we discovered that 7 to the 4 is simply 1 mod 100, we can rewrite this as 1 to the power of 505 mod 100. And then this is simply just 1. Yeah, it is pretty simple once you notice this. So the last 2 digits is 0, 1. Okay. So the last thing we'll go over in this class are some of the divisibility rules from last class that we learned. We're only going to go through some of them because most of them are pretty similar. So right now I'll be going over like 3 and like 9 and those basic ones. So if you guys remember the divisibility rules, so divisibility. It states that if the sum of all the digits is a multiple of 3, then that number is also a multiple of 3. Okay, so now we can prove that with modular arithmetic. We want to, for any number, let's just write the number as like A, B, C, D. This is all one number. So it's like a 4-digit number, such as like 1, 2, 3, 4. Where like 1 is the A, the 2 is the B, the 3 is the C, and the 4 is the D. If we take this 4-digit number, we want to find the remainder when it's divisible by 3. So we want to take this number mod 3. Right? But we can also write this number as 1000 times A plus 100 times B plus 10 times C plus D mod 3. Right? So far, so good, right? So these are all powers of 10. So we can also rewrite this as 10 cubed times A plus 10 squared times B plus 10 times C plus D. And using the fact that 10 is just simply congruent to 1, mod 3, we can rewrite this as 1 to the power of 3 times A plus 1 to the power of 2 times B plus 1 times C plus D. Mod 3. And this is simply just A plus B plus C plus D. So what this means is that this number, our original number, ABCD, has the same remainder as the sum of the digits when taken mod 3. So that means if we just check if the sum of the digits is divisible by 3, that would mean the original number is also divisible by 3. Does that make sense to everyone? Why are we talking about CSGO, guys? I guess we're ending for today. Okay, bye guys. You guys are free to leave if you want.